So this is an important session for the Society. As many of you know, the Society takes great pride in awarding PhD theses and outstanding young colleagues. This is done through a nomination process where people submit their nominations and the President appoints a committee that evaluates each nomination. And once they make a decision, they are announced. Before 3 years, we used to offer the PhD awards only once every 3 years, but since the field is growing, we have now decided to offer it every year. So that is the reason why you see 3 PhD awardees here. And this year we also had an unusual but a good situation that the committee decided that we'll have a joint winners for also the Young Scientist Award, essentially. That is for a young scientist with outstanding publications. At this point, I should also thank Paulo, Alexandra, and the organizing committee for waiving the registration fees for the award winners. And the Society supports them through a prize award and also some a travel grant. So it is, I'd like to make 2 points. Colleagues that you have, students and young researchers, please nominate them. Only if they get nominated, they get considered, so please nominate them. It's a fantastic opportunity. And the next one is for all the awardees. With great awards comes great responsibility. So we look forward for your continuous support to the Society and to pay it forward to other young people. So please engage yourself with young people. They really look up to all of you as future leaders in this Society. So the next speaker is Lukas Bingel. Lukas received his PhD from the Georgia Tech and now works for Dow in the US. Lukas, over to you.
Yep. All right. Thanks so much for the introduction. Thanks for the organizers supporting me to be here. And also thanks to the committee for selecting me for this award. So today, without any further ado, I'm going to be talking about flexible MOFs. So we've heard a lot about flexibility in adsorbents over the last few days. And I'm mostly going to be focusing on linker rotation. So why do we care about linker rotation or flexible MOFs? When we see linker rotation, we have a switch between a non-porous and a porous structure causing isotherms as shown there in the middle with a very sharp stepped isotherm with an increased usable capacity. And then also a high dependence of the position of this step on the adsorbate, suggesting a potential for separation. So that leaves us with a lot of questions to answer and a lot of stuff that I tried to attempt to answer during my PhD thesis. So that's what I'm going to be talking about today with these 3 topics or questions. So the first one is focused on how can we fit those stepped isotherms. So I took some ideas from the business world where there's this model that exists that describes how fast does an innovation penetrate into the market. And I noticed some similarities between adsorption and this model. So I came up with this equation and this isotherm that's shown in the bottom right that actually describes adsorption pretty well and models these very significant isotherm shapes. So now we have this 2-parameter model. And we tried to actually apply it to real data. So we could show that it actually fits isotherm types 1, 3, and 5 pretty well. And then we also actually looked into more relevant systems. So for example, for water adsorption, we could show that just looking at the 2 parameters, A and B, we can get some information about the hydrophilicity of our system, or if we have the same system with different pore sizes, we can just look at those parameters and get a relative idea about the pore sizes in those systems. More importantly, when we look at other flexible materials like cadmium I-13, we can see that, for example, here for methane adsorption, we can use this model to fit those isotherm shapes very well. And then we can use those continuous fits to calculate heats of adsorptions in comparison to what was done in this original paper by just using interpolation to get values that agree very well with what was published in this paper, but now using an actual isotherm model. Then also looking at IST predictions that consider stepped isotherms where we have OFAST as a method that was specifically developed for these kind of systems. And now with this 2-parameter model, we can easily fit these stepped isotherms, predict IST predictions, and they agree very well with this more complex, specifically developed OFAST system. So to kind of summarize this first part, which was one paper within my thesis, we developed an isotherm model that fits 3 isotherm types very well, and we can actually extract data out of it that help us with predictions of IST, heats of adsorption, and also give us some qualitative information about our system. So now we've only looked at single component systems so far. So the next question kind of was, how can we actually use those flexible materials to separate gases? So we tried to develop a more robust understanding for one specific system. So kind of going back to this cadmium IF13 material, which is an analog to CIF7 and CIF9, just with cadmium as the cation. And we first collected single component hydrocarbon data as shown here, where we have these very nice sharp isotherm steps and no uptake in the regime before this isotherm step. But more importantly, when we take a closer look, we can actually see if we compare propane and propylene, we see that propane has a lower threshold pressure, which indicates there's a higher affinity for the alkane over the alkene, which is very surprising but also very desired for industrial applications. So we tried to take a closer look at this and understand why does it actually behave that way. So one of my collaborators actually collected in situ synchrotron data with gas dosed here, where we can see these PRXRD pattern here with increased pressure going from bottom to top. And we can see for both adsorbents, we go through this phase transition where we go from the closed phase to the open phase. But as we can see, it occurs at different pressures for the individual components. So then, once we had those data, we took a more closer look at the actual adsorption environment in the open structure with the molecules inside. So we kind of solved or looked at where do these molecules adsorb. And surprisingly, for both components, we actually saw that carbon-hydrogen pi interactions were the desired mode of interaction. However, if we look at the 2 different materials, we can see that for propane, we have shorter distance between our bonds and also a higher quantitative number for propane, suggesting this thermodynamic selectivity, what we also saw initially from our step of the isotherms. But it's not only the material or the adsorbate that helps with the higher binding. When we actually overlaid our solved structures, we also see that our flexible material is slightly twisted depending on the specific adsorbate that we use, suggesting that our material actually also adapts to the specific adsorbate that we're looking at. And then once we used the isotherm model that I showed in the first part and compared it to DFT calculations, we actually showed that there's a higher heats of adsorption for propane over propylene, suggesting this inverse selectivity that we were looking at. So as a next step, kind of doing what Nick was just talking about with dynamic breakthrough experiments, we actually tried to see if we can actually separate propane and propylene under mixture conditions, which is shown here. However, kind of different from what Nick was just showing, in the beginning we see this slipping off effect where both components break through, and then eventually we see in the, we see here that we actually see a more traditional breakthrough where we have a separation of the 2 gases. So we use this area to calculate the different uptakes and the selectivities as seen in the other plot, where we can actually see we have, to the date when we published the paper, the highest inverse selectivity for propane over propylene. However, we still have this issue with the slipping off in the beginning. So one idea that similarly had been published in the literature before is just using an additional bed. So here we use BPL carbon, which pretty much doesn't have any selectivity for propane over propylene, and it pretty much just serves as a trap to collect all the molecules that are slipped off. And then once we do this, we actually see a very clean breakthrough curve where we can separate propane over propylene with the inverse selectivity that we desired. So to kind of summarize the second part of the talk, here we could actually show that we can use flexible MOFs to separate gases, starting from a very fundamental understanding at an atomic level, and then going all the way to actually demonstrating the downstream purification of propane and propylene with the desired inverse selectivity. So now moving on to the last third part of the talk. Sorry that I'm talking so fast, I'm just trying to get through a lot of stuff here. Yeah, how much time do I have left? Okay, perfect. So getting to the third part of the talk, where we actually try to use these findings and increase the selectivity or the separation performance. So we know for rigid frameworks, we can use linker functionalization to introduce adsorption sites that target one specific component. However, for flexible MOFs, we also know that introducing these functional groups impacts the stability of our flexible material and changes its flexibility or the threshold pressures. So the idea here was to look at biogas separation, so CO2 and methane, using CIF7, again similar to the cadmium I-13 that I showed before. And then we know we can introduce nitrogen-containing sites targeting CO2 with the idea that it doesn't impact methane too much, increasing the selectivity towards CO2 more. So here we use the post-synthetic ligand exchange approach, where we synthesized our CIF7 first and then treated it with solutions of these linkers to incorporate them in the structure. So we synthesized a lot of materials. Here I only show 4 that we used for the first part of the study, where we first used cryogenic nitrogen physisorption to compare the porosity, and then we used digestion NMR to confirm that we have around 10% of the different linkers incorporated to establish a baseline for comparison. And then we looked at PXRD data to actually confirm the crystallinity of our material. One important or interesting finding here was once we actually took a closer look at the peaks, we see a slight shift of the 2 amino sample towards lower angles, which indicates a unit cell expansion. So the bulky amine group that in there actually expands our unit cell a bit. Then we also looked at the samples under a microscope. So we used confocal laser scanning microscopy after excitation, because those different linkers emit light at different wavelengths after excitation. So we can actually see the spatial distribution of our linkers within our particles. And then we looked at it under an SEM to confirm that even after the post-synthetic ligand treatment approach, we still have a uniform crystallinity and morphology of our systems. And then moving on to the actual adsorption, which I guess is the more interesting part here. We looked at CO2 and methane adsorption just as single component isotherms first here. If we look at CO2, we see the increase, especially in the low pressure range where we introduce these specific adsorption sites for CO2. And then we see for the benzodiazole here in green that it kind of loses its flexibility, kind of switch to a type 1 isotherm and levels out much lower, which is most likely due to pore blockage, which has been reported for this material in the literature before. Similar observations for methane, where we see the slight increase in uptake and the biggest impact on the 2 amino CIF7 sample, which is most likely due to an easier diffusion due to the unit cell expansion that I talked about previously. So then we also looked at these samples again in a breakthrough setup, where we can see the increase of CO2 with pressure, but also higher uptakes for these specific materials. And if we look at those symbols here, they show the selectivity for 1 and 2 bar. We see for the 2 last sample, benzodiazole and 5-aza, we see the highest selectivity. However, since the benzodiazole, what I showed on the previous slide, loses its flexibility, we decided that the 5-aza sample is the most promising. So we moved on with that sample, synthesized more with different concentration, as shown here on the left-hand side with those symbols, where we can see the low efficiency of our approach, but we can still get 3 different samples with different concentrations, and then again confirmed crystallinity and porosity here. Then again, moving on to our adsorption data collection, where we have the single component isotherms here, where we see this very similar trend. Once we introduce more of these functional sites, we get more or higher uptake of CO2 in the low pressure range. And when we look at the sample with the highest concentration of 5-aza incorporated, we see that it again almost loses its flexibility and switches to a type 1 isotherm. And very similar for methane, we see that for this highly incorporated sample, it pretty much loses its flexibility completely. So we tried to understand why does this happen. So one of my colleagues looked into quantifying the energy of the 2 different phases, and what we could actually see is that the driving force to the open phase increases because we could see that there's increased hydrogen bonding in the open structure of the nitrogen and the heteroatom of the incorporated linker with protons from adjacent linkers stabilizing the open phase. So we have an increase in driving force for the open structure. Again, we looked at binary breakthrough data here to investigate the increase in selectivity or the change in selectivity. And we can see for the first 3 samples, CO2 uptakes increase while methane remains kind of constant for different pressures and different systems. But then for the 24% system, we can actually see that there's quite a high uptake of methane in the system as well, which then is reflected in the selectivity that's shown on the right-hand side, where still the sample from the first part of the third part of the talk, where we have the highest selectivity for the CIF7 sample with 10% ASA at 1 bar is the highest selectivity. So now we had showed this just in a single component, a single pass-through breakthrough system. So we also tried to see the actual implication on more process, on a more process view. So one of my collaborators simulated pressure swing adsorptions using these, this material, and kind of the profile is shown on the left-hand side, where we can see for the purple line is this new material. We have higher uptakes of CO2 locally, which results in a higher selectivity, and that also impacts our performance metrics as shown on the right-hand side in terms of increased productivity, recovery, and a lower energy requirement. But what we can see from the first plot on the left-hand side is also the utilization of the bed is very low. So we attempted on increasing the utilization here even more by changing the flow rate and the duration of the high pressure feed step, as shown here, where we can see these heat maps with the trade-off of if we increase productivity and energy, or in lower energy requirement, we get a penalty with purity. So we picked this point as shown in this 3 plot as the best point for optimization, and that is then also reflected in our performance metrics as shown in the bottom left corner, where we have an even further increase in terms of productivity, recovery, and energy requirement. So to summarize this last part of the talk, here we showed a strategic approach to incorporate functional groups into a system that target one specific component of the mixture, increasing the adsorption for the specific component, but then at the same time not impacting the other component too much, with a shift of the flexibility towards our desired outcome, where we have still our flexibility, but it opens up more prone towards the higher selective component. So to kind of summarize the whole talk, first we showed how we can fit these stepped isotherms. So we have a continuous model that we can use for all kind of different assessments in terms of thermodynamic assessments or just qualitative assessments. Then we took a closer look at one specific system to show that we can actually use these flexible materials to separate gases. And this was a very fun project because we can actually show that we have inverse selectivity towards a component that seems very undesired here, that propane would adsorb more likely than propylene. And then lastly, using these findings to take a step even further to increase the selectivity using this strategic post-synthetic ligand exchange approach here with actual demonstration in a process ring adsorption to show that this has a positive impact on our systems. All this work couldn't have been done without a lot of collaborators and the support of my PhD advisor. So I want to thank Krista Walton for her support, a lot of collaborators from Georgia Tech, from NREL, Colorado School of Mines, NIST, and funding from the Georgia Institute of Technology. With that, I'd like to wrap up. Thanks for your attention, and thanks again.